Welcome to the lecture 5 on renewable energy sources and applications. Myself Dr. Sharadindu Panda want to describe the different types of silicon photovoltaic cell and the monocrystalline silicon solar cell fabrication process in this lecture. First, before going to the silicon based photovoltaic cell differences or classifications, I may want to discuss some classifications of the photovoltaic solar cells in another way. That is the conventional, traditional, and the first generation solar cell, second generation solar cell, and the third generation solar cell. The solar cells made of crystalline silicon are often called the conventional, traditional, or the first generation solar cells, as they were developed in the 1950s and remain the most common type up to the present time, because they are produced from 160 to 190 micrometer thick solar wafers, that is slices from the bulks of the solar grade silicon. They are sometimes called wafer based solar cells. In the second generation solar cells or the panels are based on the thin film technology and are of commercially significant importance. These include the cadmium telluride or the CIGS and the amorphous silicon. The third generation solar cells are often labeled as the emerging technologies with the little or no market significance and include a large range of substances, mostly organic, often using the organometallic compounds. So in this lecture, I want to discuss the classification of the silicon photovoltaic cell. So the silicon photovoltaic cell is mainly divided in two ways. One is the crystalline, another is the non-crystalline silicon based solar cell. So, crystalline silicon solar cell, there is two types of solar cell, that is monocrystalline silicon solar cell and the polycrystalline silicon solar cell. Non-classified as the crystalline silicon, that is non-crystalline silicon, that is the thin film solar cell, that is silicon based thin film solar cell. It is broadly classified as the amorphous silicon solar cell, amorphous or the microcrystalline tandem solar cell, protocrystalline silicon solar cell, and the polycrystalline silicon on glass based solar cell. Now come to the monocrystalline silicon solar cell. In the monocrystalline silicon solar cell, the monocrystalline means, or the monocrystalline silicon is a form in which the crystal structure is homogeneous throughout the material. The orientation, lattice parameter, and the electronic properties are constant throughout the material. Dopant atoms such as the phosphorus and the boron are often incorporated into the film to make the silicon N-type or P-type respectively. Monocrystalline silicon is fabricated in the form of silicon wafers, usually by the Czochralski method, I will discuss later, and can be quite expensive depending on the radial size of the desired single crystal wafer. This monocrystalline material, while useful, is one of the cheap expenses associated with producing the photovoltaics, where approximately the 40% of the final price of the product is attributable to the cost of the starting silicon wafer used in the solar cell fabrication. So this is the monocrystalline type of solar cell. To make the monocrystalline solar cell, silicon is formed into the bars and cut into the wafers. These type of cells are called the monocrystalline to indicate that the silicon used is single crystal silicon. Because the cell is composed of a single crystal, the electrons that generate a flow of electricity have more room to move. As a result, the monocrystalline silicon solar cells are more efficient than their polycrystalline counterparts. Now come to the polycrystalline silicon solar cell. The polycrystalline silicon is composed of many smaller silicon grains of varied crystallographic orientation, typically greater than 1 millimeter in size. This material can be synthesized easily by allowing liquid silicon to cool using a seed crystal of the desired crystal structure. Additionally, other methods for forming the smaller grain polycrystalline silicon exist, such as high temperature chemical vapor deposition, that is CVD technique. So this is the polycrystalline based silicon solar cell. The polycrystalline based silicon solar cells, also known as the polysilicon and the multisilicon cells, where the first solar cells ever introduced in the industry in 1981. Monocrystalline was established in 1950, and then the polycrystalline silicon solar cell was introduced in the industry in 1981. Polycrystalline silicon solar cells do not go through the cutting process used for the monocrystalline cells. Instead, the silicon is melted, which is to produce the monocrystalline silicon, and poured into a square mold, hence the square shape of the polycrystalline. In this way, they are much more affordable since hardly any silicon is wasted during the manufacturing process. However, the polycrystalline is less efficient than its monocrystalline cousin. Typically, the polycrystalline solar photovoltaic system operated at a 13 to 16% efficiency. Again, this is due to the fact that the material has a lower purity. Due to this reality, the polycrystalline is less space efficient as well. One other drawback of the polycrystalline is that has a lower heat tolerance than the monocrystalline, which means they don't perform as efficiently in high temperatures. Now come to the very important type of silicon solar cell, that is the second generation solar cell, that is thin film silicon solar cell. A thin film solar cell is a second generation solar cell that is made by depositing one or more thin layers or thin film of the photovoltaic material on a substrate such as glass, plastic or metal. Thin film solar cells are commercially used in several technologies including cadmium telluride, copper indium gallium diselenite and the thin film silicon, that is A silicon or TF silicon. The film thickness varies from a few nanometers to the tens of micrometers, much thinner than the thin films rival technology. The conventional first generation crystalline silicon solar cell, that is C silicon, that uses wafers of up to the 200 micrometer thick. This allows the thin film cells to be flexible and lower in weight. It is used in building, integrated photovoltaics, and as the semi-transparent photovoltaic glazing material that can be laminated onto the windows also. The thin film technology has always been cheaper but less efficient than the conventional CCSI technology. However, it has significantly improved over the year. Now the amorphous silicon type thin film solar cell. Amorphous silicon is a non-crystalline allotropic form of silicon. This type of thin film cell is mostly fabricated by a technique called plasma enhanced chemical vapor deposition, that is PECVD. The amorphous silicon has no long range the periodic order. The application of the amorphous silicon to photovoltaics as a standalone material is somewhat limited by its inferior electronic properties. When paired with the microcrystalline silicon in tandem and the triple junction solar cells, however, the higher efficiency can be attained than with the single junction solar cells. It uses a gaseous mixture of the silicon and the hydrogen to deposit a very thin layer of only 1 micrometer of silicon on a substrate such as glass, plastic or metal that has already been coated with a layer of transparent conducting oxide. Other methods used to deposit the amorphous silicon on a substrate including sputtering and hot wire chemical vapor deposition technique. ASI, that is amorphous silicon, is attractive as a solar cell material because it's an abundant non-toxic material. It requires a low processing temperature and enables a scalable production upon a flexible low-cost substrate with little silicon material required. Due to its band gap of 1.7 electron volt, the amorphous silicon also absorbs a very broad range of light spectrum that includes the infrared and even some ultraviolet and performs very well at the weak light. This allows the cell to generate the power in the early morning or late afternoon and on cloudy and rainy days, contrary to the crystalline silicon cells that are significantly less efficient when exposed as diffuse and indirect daylight. The amorphous silicon solar cell, the basic structure of this type of solar cell is the PIN junction, that is the P-type insulator and the N. The amorphous structure of a silicon implies the high inherent disorder and dangling bonds, making it a bad conductor for charge carriers. These dangling bonds act as the recombination centers that severely reduce the carrier lifetime. A PIN structure is usually used as opposed to the NIP structure. This is because the mobility of the electrons in a amorphous silicon H is roughly 1 or 2 orders of magnitude larger than that of the holes. Thus, the collection rate of the electrons moving from the N to P-type contact is better than the holes moving from the P to N-type contact. Therefore, the P-type layer should be placed at the top where the light intensity is stronger so that the majority of the charge carriers crossing the junction are electrons. Now the second type of silicon-based thin film solar cell is amorphous or microcrystalline tandem solar cell. A layer of amorphous silicon can be combined with the layer of other allotropic forms of silicon to produce a multi-junction solar cell. When only two layers, that is two PN junctions, are combined together, then it is called a tandem cell. By stacking these layers on top of the one another, a broader range of the light spectra is absorbed, improving the cell's overall efficiency. The nanocrystalline silicon, sometimes also known as the microcrystalline silicon, is a form of the porous silicon. It is an allotropic form of silicon with the paracrystalline structure, is similar to the amorphous silicon in that it has an amorphous phase. Where they differ, however, is that the NC silicon, that is nanocrystalline silicon, has the small grains of the crystalline silicon within the amorphous phase. This is in contrast to the polycrystalline silicon, which consists solely of crystalline silicon grains separated by the grain boundaries. The difference comes solely from the grain size of the crystalline grains. Most materials with the grains in the micrometer range are actually the fine-grained polysilicon, so the nanocrystalline silicon is a better term. The term nanocrystalline silicon refers to a range of materials around the transition region from the amorphous to the microcrystalline phase in the silicon thin film. The nanocrystalline silicon, which I already described, it is the allotropic form of the silicon with paracrystalline structure, is similar to the amorphous silicon in that it has an amorphous. In the micromorphous silicon, a layer of microcrystalline silicon, that is μc Si, is combined with the amorphous silicon, creating a tandem cell. The top of the amorphous silicon layer absorbs the visible light, leaving the infrared part to the bottom microcrystal silicon layer. Because all the layers are made of silicon, they can be manufactured by the PECVD techniques. The band gap of the silicon is 1.7 electron volt and that of the Si is 1.1 electron volt. That is, the crystalline silicon is 1.1 electron volt and for the amorphous silicon the band gap is 1.7 electron volt. The Si silicon layer can absorb the red and the infrared. The best efficiency can be achieved at the transition between the amorphous silicon and the Si silicon. As the monocrystalline silicon has about the same band gap as the crystalline silicon, then the nanocrystalline silicon can replace the crystalline silicon. The micromorph stacked cell concept was pioneered and patented at the Institute of Microtechnology of the Nautical at the Neuchâtel University in Switzerland and was licensed to the TEL Solar. A new world record photovoltaic module based on the micromorph concept with the 12.24% module efficiency was independently certified in the July 2014. Now the protocrystalline silicon based thin film solar cell. The protocrystalline silicon has a higher efficiency than the amorphous silicon and it has also been shown to the improve stability but not eliminate it. The protocrystalline silicon phase is a distinct phase occurring during the crystal growth which evolves into a microcrystalline form. The protocrystalline silicon also has a relatively low absorption near the band gap owing to its more order crystalline structure. Thus, the protocrystalline and the amorphous silicon can be combined in the tandem solar cell, where the top layer of the thin protocrystalline silicon absorbs the short wavelength light, whereas the longer wavelengths are absorbed by the underlying amorphous silicon substrate. A new attempt to fuse the advantage of the bulk silicon with those of the thin film devices is thin film polycrystalline silicon on glass. This is the another type of silicon based thin film solar cell. These modules are produced by depositing an anti-reflection coating and doped silicon onto the texture glass substrates using the plasma enhanced chemical vapor deposition, that is PECVD. The texture in the glass enhances the efficiency of the cell by approximately 3% by reducing the amount of incident light reflecting from the solar cell and trapping light inside the solar cell. The silicon film is crystallized by an annealing step, temperatures of 400 to 600 Celsius, resulting in polycrystalline silicon. These new devices show the energy conversion efficiencies of 8% and the high manufacturing yields of greater than 90%. Crystalline silicon on glass, that is CSG, where the polycrystalline silicon is 1 to 2 micrometers, is noted for its stability and the durability. The use of thin film techniques also contributes to a cost saving over the bulk photovoltaics. These modules do not require the presence of a transparent conducting oxide layer. This simplifies the production process twofold. Not only can this step be skipped, but the absence of this layer makes the process of constructing a contact scheme much simpler. Both of these simplifications further reduce the cost of production. Despite the numerous advantages over the alternative design, the production cost estimations on a per unit area basis show that these devices are comparable in cost to single junction amorphous thin film solar cell. So now come to the second part of my lecture, that is monocrystalline solar cell fabrication. First step is the purifying the silicon. The silicon dioxide is either quartz, gravel or crushed quartz is placed into an electric arc furnace. A carbon arc is then applied to release the oxygen. The products are carbon dioxide and the molten silicon. At this point, the silicon is still not pure enough to be used for the solar cells and requires the further purification. The 99% pure silicon is purified even further using the float zone technique. This is the float zone technique. A rod of impure silicon is passed through a heated zone several times in the same direction. This is the actual silicon, and this is the heater wearing, and this is the molten zone. This is the rotating and pulling schemes are there. This procedure drags the impurities towards the end with each pass. This is the impurities. At a specific point, the silicon is deemed pure and the impure end is removed. Here this is the impure end and this is the pure end. So this is the pure silicon and this is the pure silicon and this is the impure silicon. Now making the single crystal silicon. Solar cells are made from the silicon balls, polycrystalline structures that have the atomic structure of a single crystal. The most commonly used process for creating the bowl is called the Czochralski method. In this process, a seed crystal of the silicon is dipped into the melted polycrystalline silicon. Here this is the Czochralski furnace where the polycrystalline silicons are there. Now it is placed into this chamber. Here this is the electrode, this is the spill tray, this is the crucible support, here the crucible. Okay, so in that crucible the wafers are melted. Okay, and this is the quartz crucible. This is the quartz crucible actually. When this is the seed crystal are dipped into the melted silicon and it is rotating and pulling out. So as the seed crystal is withdrawn and rotated, a cylinder type ingot or the bowl of the silicon is formed. This is the cylinder type, this is the rotating, this is the pulling, and this is the rotating type. So when it is pulled up and rotating, then the cylindrical shape of the ingot is produced. The ingot withdrawn is unusually pure because the impurities tend to remain in the liquid. So what is the step? The polysilicon are melted in the crucible, then the seed crystal are dipped into the melted silicon, then rotating and pulling the seed crystal, then we will get the cylindrical type ingot. Then we will get the monocrystalline cylindrical type ingots. After that we will get finally this type of cylindrical type ingots. Wafers. From the bowl, the silicon wafers are sliced and we will get only about the 1/2 of the silicon is lost from the bowl to the finished circular wafer. More if the wafer is then cut to be rectangular or hexagonal. The rectangular or hexagonal wafers are sometimes used in solar cells because they can be fitted together perfectly, thereby utilizing all available space on the front surface of the solar cell. The wafers are then polished to remove the saw marks. It has recently been found that the rougher cells absorb the light more effectively. Therefore, some manufacturers have chosen not to polish the wafer. So, final wafer produced after polishing, cleaning and the inspection. Now, to form the p-type or n-type silicon, then the doping is necessary. This doping was done in the oxidation chamber through diffusion process. The dopant impurity atoms such as boron can be added to the molten silicon in precise amounts to dope the silicon, thus changing it into the p-type silicon with the different electronic properties. This is the diffusion or the oxidation chamber. The wafers are then sealed back to the back and placed into the furnace to be heated to slightly below the melting point of the silicon, that is 2570 degrees Fahrenheit or 1410 degrees Celsius in the presence of phosphorus gas. This is the wafers are stacked into a quartz boat, okay, and it is put in the heated chamber, oxidation chamber. The phosphorus atoms burrow into the silicon, which is more porous because it is close to becoming a liquid. The temperature and the time given to the process is carefully controlled to ensure a uniform junction of the proper depth. A more recent way of doping silicon with phosphorus is to use a small particle accelerator to shoot the phosphorus ions into the ingot. By controlling the speed of the ions, it is possible to control their penetrating depth. This new process, however, has generally not been accepted by commercial manufacturers because this is very much costly. Now, placing the electrical contact to create the contacts of the photovoltaic cells. The electrical contacts connect each solar cell to another and to receiver of the produced current. The contacts must be very thin, at least in the front, so as not to block the sunlight to the cell. Metals such as palladium, silver, nickel or copper are vacuum evaporated through a photoresist, silk screened or merely deposited on the exposed portion of the cells that have been partially covered with the wax. This is the metal contact grid. This is the N-type silicon, this is the P-type silicon, and on the upper portion of the silicon solar cell, that is, there is an anti-reflection coating is also there. So for producing a metal contact, the metal like the palladium, silver, nickel or copper are deposited through the evaporation method. All the three methods involve a system in which the part of the cell on which a contact is not desired is protected, while the rest of the cell is exposed to the metal. After the contacts are in place, the thin strips, that is fingers, are placed between the cells. The most commonly used strips are the tin coated copper. Now placing the anti-reflecting coating. Because of pure silicon is shiny, it can reflect up to 35% of the sunlight. To reduce the amount of sunlight lost, an anti-reflective coating is put on the silicon wafer. The most commonly used coatings are titanium dioxide and the silicon oxide, though others are used. So as the anti-reflectant coating, the titanium dioxide and the silicon oxide is used. The material used for coating is either heated until its molecules boil up and travel to the silicon and condensed, or the material undergoes the sputtering. In this process, a high voltage knocks molecules off the material and deposits them onto the silicon at the opposite electrode. Yet another method is to allow the silicon itself to react with the oxygen or the nitrogen containing gases to form the silicon dioxide or the silicon nitride. Commercial solar cell manufacturers use the silicon nitride. Now the very much important step to produce, and the final step to produce the silicon solar cell, is the encapsulating the cell. The finished solar cells are then encapsulated, that is sealed into the silicon rubber or the ethylene vinyl acetate. This is the ethylene vinyl acetate. This is mainly used. The encapsulated solar cells are then placed into the aluminium frame. This is the aluminium frame. This is the aluminium frame. And that has a mylar or Tedlar backsheet. This is the mylar backsheet. This is the mylar backsheet or the Tedlar backsheet, and a glass or the plastic cover. Now at last there is a comparative study of the monocrystalline and the polycrystalline and the amorphous, that is thin film solar cell. Most efficient, the monocrystalline silicon solar cells are most efficient with the maximum efficiency of 21%. Polysilicon is the less efficient with the 16% efficiency, and the thin film solar cells are the 12% efficiency. Manufacture the monocrystalline silicon panels are manufactured from the single silicon crystal. Polysilicon panels that are manufactured by fusing different crystals of the silicon. Thin film, the manufactured by depositing one or more layers of the photovoltaic materials on the substrate. Monocrystalline silicon panels performance best at the standard temperature. Polysilicon performance best at the moderately high temperature, but for the thin film panels the performance best at the high temperatures. Monosilicon requires least area for the given power. Polysilicon type of solar cell requires less area for the given power, and the thin film solar cells performs best at the large area for the given power. Large amount of silicon hence has embodied energy in the monocrystalline silicon panels. Large amount of silicon hence high embodied energy in the polysilicon panels. Thin film have the low amount of silicon used, hence low embodied energy. For the monocrystalline silicon panels, the performance degrades in the low sunlight condition. For the polysilicon solar cells, the performance degrades in the low sunlight conditions, but the thin film type of solar cells performance less affected by the low sunlight conditions. The cost for the monocrystalline silicon solar cell is 1.589 USD. Polysilicon is 1.418 USD and 0.67 USD for thin film. This is the average cost actually. The largest manufacturer, SunPower USA, is the largest manufacturer for the monocrystalline silicon panels. Suntech for the polycrystalline silicon panels of China, and Fast Solar of the USA is the largest manufacturer for the thin film type of solar. As the performance, the optimum operating voltage for monocrystalline is 17.82 volt, for polycrystalline 17, for thin film 18 volt. Optimum operating current, that is 0.285 for monocrystalline, 0.29 ampere for polycrystalline, and 0.278 ampere for the thin film. Short circuit current, that is 0.315 ampere for monocrystalline, 0.35 for polycrystalline, and 0.4 ampere for the thin film. The maximum power, that is for monocrystalline, that is 5 watt Pmax, polycrystalline 5 watt, thin film is also 5 watt. The module efficiency for monocrystalline is 16.2%, polycrystalline 14, and thin film is nearly 12. Temperature coefficient of the Pmax is minus 0.549%, that is 0.43 for polycrystalline and 0.19 for the thin film amorphous. The maximum system voltage for monocrystalline, that is 1000 VDC, for polycrystalline 600 VDC, and thin film is 600 VDC. So these are the references. Thank you.